Hello, I am Gabriela Abeledo. Today I am going to present the work titled Grain Yield and Quality Trace Variability in Bread Weights under Contrasting Nitrogen Availability, Leverage Point for Resilient Production Systems. This work was carried out together with Miguel Magmani and Daniel Miralles from the University of Buenos Aires and IFEBA CONICET, Argentina. The first point is to introduce the concept of quality. It's a multidimensional concept when a product is superior in relevant characteristics, combining both objective metrics and subjective final assessments. In the case of bread wheat, quality can be evaluated at different points along the value chain. Grain yield is the main indicator of field productivity. At the base of the chain, grain quality depends on commercial parameters like moisture content, test weight, and protein concentration. As we move down the value chain, quality shifts toward technological traits, gluten content, flour extraction, and dough strength determine potential uses of the flour. Finally, at the consumer level, quality is expressed in the end of products, bread, cookies, pizza, or gluten-based foods. Ensuring a stable wheat production and end-use quality under increasing environmental uncertainty is a major challenge for global food security. Nitrogen management and cultivar selection are key practices to reduce production and quality risks. However, the combined effects of variability across the wheat value chain remain poorly quantified. Given this context, the objective of our study was to assess how soil nitrogen availability and cultivar quality group shape the variability and interrelationships among grain yield, grain protein concentration, industrial quality, and baking attributes in bread wheat. Now I will describe the methodology of the study. The experiment was carried out at the School of Agronomy, University of Buenos Aires, Argentina. We evaluated 6 bread wheat cultivars belonging to 3 quality groups. Quality group 1 corresponds to high bread making quality, quality group 2 to regular quality, and quality group 3 to low bread making quality. The experiment included 3 soil nitrogen availabilities: 70, 160, and 240 kilograms of nitrogen per hectare. The experiment was conducted over 3 growing seasons. The experimental design was a randomized complete block design with 3 or 4 replicants. The crop was grown under irrigation with full control of weeds, pests, and diseases. The following variables were measured at harvest: at the field level, grain yield; at the commercial quality level, grain protein concentration; at the processing level, wet gluten content and dough strength; and finally, at the consumer level, loaf volume. To estimate grain yield, we sampled spikes along a 2-meter row. The spikes were then threshed, and the final yield is expressed on a dry basis in kilograms per hectare. We also performed an extra harvest to evaluate quality trace, meaning the grains in a Buehler experimental mill. Grain protein concentration was determined by microculture. Following local commercial norms, we express grain protein concentration on a 13.5% moisture basis. Wet gluten content was measured using the glutomatic method, while dough strength represents the W parameter from the albograph test. To determine loaf volume, we follow a standardized baking test protocol. We can break this process down into 5 main steps. First, we mix the obtained flour with water, salt, sugar, and yeast. Second, the dough went through that pre-fermentation and fermentation stages. Third, the dough was kneaded and shaped. Fourth, the dough was baked into a standardized loaf. And finally, we measure the loaf volume. Loaf volume was measured by the Repside displacement method. Let's look at the results. The first section of the results focusing on grain yield variability. This figure shows the cumulative frequency distribution of grain yield combining all cultivars, nitrogen levels, and growing seasons. The x-axis shows grain yield in kilograms per hectare, and the y-axis shows the cumulative frequency. The overall range of variation was very wide, reflecting the high variability across environments and treatments. Looking at the key values of this distribution, the mean yield was 6,073 kilograms per hectare. The 80th percentile, meaning the value below which 80% of the observations fall, was 7,811 kilograms per hectare. The median was 6,076 kilograms per hectare, and the 20th percentile was 4,262 kilograms per hectare. This wide range from around 4,000 to nearly 8,000 kilograms per hectare across percentiles reflects the strong influence of the treatment on growing seasons and on yield. This figure shows grain yield distribution across treatments. On the left, yield is shown by cultivar group. The darker the symbol, the higher his bread making quality classification. On the right, yield is grouped by nitrogen treatment, with darker symbols indicating higher initial nitrogen availability. Regarding the quality groups, moving from a quality group 1 cultivar to a quality group 2 allow us to increase yields by approximately 940 kilograms per hectare on average, which is about a 17% increase. Specifically, we saw increases of nearly 600 kilograms per hectare for the 20th percentile, 1,400 for the median, and 1,800 for the 80th percentile. In relative terms, these increases scale up from 17% to 28% as we move from the 20th to the 80th percentile. Thus, we can see that both the cultivar type and the nitrogen availability level condition the grain yield achieved. Quality group 2 and quality group 3 cultivars reach higher yields than quality group 1, particularly at the upper percentiles of the distribution. Higher nitrogen availabilities shift the distribution toward higher yield values, reducing the probability of low yield scenarios. The second section of the results focuses on grain protein concentration variability. This figure shows the cumulative frequency distribution of grain protein concentration combining all cultivars, nitrogen levels, and growing seasons. As with grain yield, protein concentration shows a wide range of variation across the experiment. The distribution ranged from values around 7% up to over 15%. Looking at the key values of this distribution, we can see that the mean protein concentration was 9.5%. The 80th percentile was 10.9%, the median was 9.4%, and the 20th percentile was 8.1%. These values highlight that a large proportion of the observations fell below the minimum protein level typically required for high bread making quality, 11%. As you can see in the table, protein values are also reported on a dry weight basis. These values are higher as expected since no moisture is accounted for. When we separated this distribution by treatment, both the cultivar type and the nitrogen availability regulated the variations in protein concentration. Regarding cultivar quality group for the median condition, moving from a quality group 1 to a quality group 2 increased protein by nearly 1 percentage point. Quality group 1 maintained consistently higher protein levels across all percentiles, around 10% higher than quality group 2. Regarding nitrogen availability, increasing nitrogen from 70 to 240 kilograms per hectare raised mean protein concentration by 21%, with similar increases across all percentiles. This confirms that nitrogen availability was the primary driver of protein concentration, while cultivar group modulated the baseline protein level. Now I will move on to the industrial quality results, where gluten content and dough strength were the variables under analysis. I will start analyzing the effect of the treatments on wet gluten. This figure shows the relationship between wet gluten content and grain protein concentration, pulling all cultivars and nitrogen levels. As protein concentration increased, wet gluten content also increased in a linear way. This confirms that protein concentration was a strong predictor of gluten content across the range of conditions evaluated. This figure shows the relationship now separated by cultivar quality group. All three quality groups show a similar relationship between protein and gluten content. Nitrogen availability expanded the range of protein concentrations explored, and therefore also the range of gluten values achieved. Thus, the cultivar, and especially the nitrogen, impose a ceiling on the amount of gluten achieved. Now I will move on to the analysis of dough strength, which was the other industrial quality variable under evaluation. In this slide, we can see the relationship between grain protein concentration on the x-axis and dough strength, which was measured as the W value from the allograft test on the y-axis. As shown by the regression line, there is a positive and high significant linear relationship between both variables. with a p-value of less than 0.001. The equation indicates that for each percentage point increase in grain protein, dough strength increases by 46 units. However, the R-square value of 0.34 reminds us that protein concentrations alone explain 34% of the total variance in dough strength, meaning other factors are also at play. However, when we separate the data by cultivar quality group, a clear pattern appears. Quality group 1 achieved significant higher dough strength values at the same protein concentration compared to quality group 2 and 3. This means that the three quality groups follow distinct but parallel trajectories, where quality group 1 achieved more dough strength for the same amount of protein. Additionally, nitrogen availability acts by modifying the range of protein concentrations explored, that is, by shifting the system along the relationship. Putting all together, cultivar type and nitrogen availability regulate dough strength through different pathways. The cultivar acts by modifying the W versus protein relationship, that is, by changes how much dough strength was produced per unit of protein, while the changes in dough strength in response to nitrogen were mediated by the range of protein explored. I will now move to the last quality trait, loaf volume. This variable can be seen as the final expression of grain quality along the wheat value chain. In this slide, we show the relationship between loaf volume and dough strength using all the data combined across cultivars, nitrogen levels, and years. Overall, loaf volume increased with increasing dough strength, indicating a clear and positive association between these two variables. Thus, dough strength was a good determinant of bread volume. Stronger doughs were generally able to retain more gas during baking, resulting in larger loaf volumes. When the data are separated by cultivar, a clear pattern becomes visible. Cultivars belonging to quality group 1 consistently achieved the highest loaf volumes. This was mainly explained by their higher dough strength compared with cultivars from quality groups 2 and 3. In this slide, the same relationship is shown, but separating the data by nitrogen availability. Nitrogen supply mainly affected the range of dough strength values that were achieved, and therefore the range of loaf volumes. At higher nitrogen availability, higher dough strength and larger loaf volume were more frequently observed. This shows that nitrogen acts by expanding the potential quality, while the cultivar determines how efficiently that quality was translated into loaf volume. In conclusion, nitrogen availability appears as the main driver of yield and protein stability. However, cultivar quality group play a key role in determining how protein was translated into industrial quality and baking performance. In other words, nitrogen mainly affected the quantity of protein, while the cultivar determined its functionality. This combined approach can help improve both productivity and end-use quality under variable growing conditions, enhancing resilience along the wheat value chain. Thank you very much for your attention.